All right, guys. So you just finished watching part one of the free response. We went through the long form questions 1 through 3, and now we're gonna get back into it with question 4. Now remember, these are the shorter questions. So question 4, 5, and 6, 4, 5, 6, and 7 are all worth 4 points. And a lot of them had 4 prompts, so it's just kind of 1 point per question. Okay, so let's go ahead and check out the rest of this. Okay, so we have another calorimetry question. Okay, so it starts off, gives us the calorimetry data, and it just wants to take a temperature reading here on the thermometer. So remember, don't forget that estimated digit. So each tick mark here represents the ones place, so like 30, 31, 32, 33, 34, 35, 36, 37, 38, 39. So we're allowed to estimate to the tenths place. So if you just wrote 38 or you just wrote 39 and that's it, you're wrong. I say 38.5. I'm sure they would allow 38.4. Make sure you include your units. Don't just say 38.5. Say 38.5 degrees Celsius. I'm not sure if they take off if you didn't put degrees Celsius though. The main thing is making sure you have that estimated digit. All right. All right. So this one is just to show, what happens to the speed of the water molecules as this happens. So understand what happened here. We took a metal cube and we heated it up to 100 degrees Celsius, and then we put it into room temperature water. So the heat from the metal is going to transfer to the water. So the metal is going to cool down and the water is going to heat up until they reach that equilibrium temperature. And this was the equilibrium temperature. So that would be 38.5 there. And, just concepts to remember, just because the water did not increase in temperature as much as the metal decreased in temperature, it's still the same amount of heat being transferred. It's just they would have, the metal probably has a much lower specific heat capacity. So anyway, so the water is absorbing energy, and so it would be speeding up, and so we just have to draw some longer arrows. So each of the water molecules would just be going faster. Okay. Yeah. So here it was just use the information to calculate the heat capacity for the metal. So Q equals MCAT, but we're solving for C. So C equals Q over MAT. So Q is 2940. Okay. Our mass of our metal was 98.1 grams. And the temperature change for the metal was 100 minus 38.5. Now that's the absolute value. It's really 38.5 minus 100, but then this would be a negative sign here, and then we would have a negative divided by negative. You should not have a negative specific heat capacity. Okay, so that's why I'm just using the absolute value of the temperature change. Okay, and so that comes out to be around 0.487 joules per gram degree Celsius for our heat capacity. Okay. Now, I think they would read down, so if you didn't get the right answer here, but you used it properly here, you'd get credit. Okay. And then, so in a second experiment, the same amount of thermal energy is transferred from 98.1 grams of aluminum with a specific heat of 0.897. So notice that this specific heat capacity for aluminum is higher than the specific heat capacity for this metal. And they want us to know if the delta T for the aluminum would be greater than, less than, or equal to, I guess, basically, the delta T from this metal sample. So remember, the higher the heat capacity, the kind of more energy has to be released for it to cool down, and or the more energy has to be absorbed for it to heat up. So the higher the heat capacity, the less fluctuations it will have with temperature change. So we should expect the aluminum sample will have less of a temperature change because it has a higher specific heat capacity compared to what we calculated in part C. So if you calculated a number greater than this and you said a aluminum sample will have more of a temperature change, then you'd probably be right there. Okay, again, they would read down. but it's just because the aluminum has a higher specific heat capacity, and this gives it a higher tolerance for temperature change. Okay. Moving on to question 5. Sorry, I didn't write that at the top of my thing. So let's see. Question 5 is 1, 2, 3, 4 prompts. So question 5 has 4 prompts, so each one is worth a point. So first one, just write the equilibrium expression for this reaction. So that's hopefully an easy one. Okay. Now this one might be a little tough, but they give us a Q value, and then they ask us to complete the particle diagram. So they gave us the particles of the reactants that are in the mixture, but we don't know. We have to draw a number of HI molecules to complete the diagram here. And they tell us Q at this moment in time is equal to 0.67. So remember, Q is equal to the same expression as K. And so what I would just assume that I would just say, okay, let the number of each particle be its molarity. So I'm going to say the molarity of HI is 3, and the molarity of I2 is 2. And I would just say Q, which is the same thing as K, but just not at equilibrium. 0.67 equals x squared over 3 over 2. If you do that, it comes out to be x equals 2, or essentially 2. So you need 2 HI molecules. So you had to draw 2 HI molecules in the diagram there. Okay. All right, and then part 2 here is basically Le Chatelier's principal question. They want us to change something that would give us more HI. So notice here, when equilibrium gets reached, we have this many moles of HI, and they want us to say what change could have caused this jump in the equilibrium, so to the moles of HI to increase. So really, it's what would cause the reaction to shift to the right. Okay. There's probably 3 possible answers. The one I went with was decrease in temperature because it was an exothermic reaction. Okay, so if you decrease the temperature, the reaction is going to shift to the right because you can think of heat as a product, and if you remove heat, the reaction will shift to replace the heat, and in this case, it would be on the right side because it was a negative delta H. So that's the one I thought of. The other 2 possible choices would be if you just add more H2 or add more I2. So I'm guessing if you said add more I2 to the system, that would be 1 point. That would work. Or add more H2 to the system, that would be another thing that would work. The first one for me that came to mind was a decrease in temperature because it was exothermic. And I think I was thinking of ways to shift the reaction because it said we couldn't add any HI. So I was thinking, without adding something, what could cause the shift? So that's why I went to the decrease in temperature. But if you said adding more HI or adding more I2, that would work as well. And notice it doesn't say explain or justify. So don't, And then part 3, after equilibrium is established, the mixture is transferred in a larger container. So remember, right, 2 moles of gas on this side, 2 moles of gas on that side. So changing the volume, which would be a change in pressure, will not cause a Le Chatelier's shift in this reaction because moles of gas are equal. So it's going to remain the same. The moles of HI are going to remain the same. All the partial pressures are going to decrease, but there's going to be no shift. So moles of HI would remain the same. The change in overall pressure will not cause a shift in the equilibrium because moles of gas are equal on each side, or delta N is 0. Okay. All right, question 6. Another 4 prompter, so 1 point apiece. Okay. So here they give us the natural log of conservation versus time graph, 1 over the concentration versus time graph. That's a straight line, so we know it's second order. They tell us it's second order in the rate equation they give us here. And they're saying in part A, explain how the graphs indicate the reaction is second order with respect to NO. And I would say the 1 over concentration versus time graph gave us a straight line or a constant slope, and that means it's second order. Now, it says graphs plural, so you might need to have mentioned that it's not first order because the natural log of concentration versus time graph did not give us a straight line, but they didn't give us that much space here, so I'm thinking that this would be good enough. And then part B, we're just doing some stoichiometry. We have the rate of disappearance of NO2, and if we go to the equation, they're asking us for the rate of appearance of oxygen. It's not going to be the same rate because it's a 1-to-2 ratio. So we have to take the rate of NO2 and multiply it by 1 and divide it by 2, and that would give us the rate of O2. Okay, so we take the given rate, multiply it by a ratio 1/2, and that'll give us the rate of the appearance of oxygen. Okay, and it would have the same units as the rate of disappearance for the NO2. Okay, and then here, they give us the dot structure of NO2, and then they ask us here to draw the dot structure of NO2 plus. Okay, remember, plus means you lost an electron, and so all you really have to do is take that electron away, and then try to figure out how to satisfy the octet rule for nitrogen. And so really, it's just take that dot away, and then take the lone pair here from this oxygen and make it a double bond. Okay. So we'd have 2 lone pairs on each oxygen and 2 double bonds between the nitrogen, and that would work. Okay. There's probably other, like if you had a triple bond here with 1 lone pair and then a single bond here with 3 lone pairs, I'm guessing they would give you credit for this, but this would be the better way to do it. Especially for formal charge purposes, but they didn't say anything about formal charge, so you don't have to worry about that. Okay, and then a student says that the bond angles are different, and do you agree or disagree? Based on my drawings, I would agree. This has 3 domains of electrons around the central atom. This has 2 domains, so this bond angle will be 180. This bond angle will be more like 120. Okay, so definitely different bond angles. Now, if you have more domains over here, if you had 3 domains here and 3 domains here and you said disagree, then you might get credit for that, but you have to justify. Okay, so you'd have to have the right justification. Say they have equal amount of domains around the central atom, something like that. That would be fine. All right, and then we move on to question 7. Let's see, question 7 had 1, 2, 3 prompts. I'm guessing this is going to be the 2.1 because you had 2 steps to fill in. Okay, so here would just be, liters times molarity times molar mass gives us how many grams of the solid we're going to have to measure out. And so that would just be our calculation there. And then here we have to identify the steps. And I know some of you might have struggled with this a little bit because, essentially it's weigh out the solid, put it in the volumetric flask, fill it up with water, and make sure all of it dissolves. But they kind of have it spaced out here. So step 2 would be you need to add the solid to the flask. And then if you look at step 3, it says swirl the mixture to dissolve. And then step 4 would be fill to the line with distilled water. And then step 5 would be make sure it's a homogeneous mixture. So understand that should have been a clue that step 2, add solid and some distilled water to the volumetric flask. Okay, so you can add some distilled water and then transfer the solid to the volumetric flask. Okay, and then once all the solids dissolved, then you can fill it up to the line with distilled water. Okay, maybe fill it up to the line so that the meniscus is, the bottom of the meniscus is at the line. Okay, something like that. And then, shake until it's a solution. Okay. So as long as you had something, along those lines, you're probably good to go. Okay. And then, hey, we just talked chromatography. So what are the odds? But anyway, this really had nothing to do with chromatography, and it was more just like, if things are traveling at the same rate and you give them less time to separate, they wouldn't be as separated. That's essentially what it comes down to. So, right? So again, both dots would have started at the same place, and as they move through the paper with the solvent, they're separating based on their interactions with the paper versus their interactions with the solvent. And so if you did the same exact experiment, but you stopped after 15 minutes instead of 30 minutes, there wouldn't be as much time for them to separate, assuming that you did everything the same, so they would have the same rate of separation as the reaction proceeded. If you gave them less time, they would be closer together when you stopped the reaction. So the separation distance should be shorter if you did it 15 minutes instead of 30 minutes because they had less time to separate. So anyway, so even if you really didn't know much about chromatography, pretty easy question to answer. All right. So,